Well, let's start our lecture number 20 and our summary for today's lecture. We are going to show how Maxwell's equation predict the propagation of electromagnetic disturbances in space, how the electric and magnetic field couple and one feeds the other and they propagate together in space. So we're going to talk about the homogeneous wave equation. We're going to derive the general solution in rectangular coordinates, and also we are going to, that's going to be a general solution independent on the way the fields vary with time. And then we are going to derive Maxwell's equations for harmonic fields. And today's class is not going to be a very long one too, as well. So the references for this lecture are our ebook, Chapter 7, Sections 7.1 and 7.2, and Jackson's Classical Electrodynamics, Section 7.1. Let me just fix here. Is not the draft, right? Section 7.1. Right here, sections. Section. Let's make a copy of this. So, you know that Maxwell's in his treatise on the theory of the dynamics, on the dynamics of the electromagnetic field, that was published in 1865. He was, he assembled, as we demonstrated along these lectures, he assembled all the experimental effects and phenomena involving the electric and magnetic fields and assembled those in a set of equations. They were not originally 4 equations, there were several equations. Only afterwards that Heaviside was able to use this this Nabla notation and start to compacting the equations. But it was interesting. He was he demonstrated by use of these equations that electric and magnetic fields could couple together, and one feeds the other one. They would propagate in space with the speed of light, right? And interestingly, at that time, people thought that the velocity of light depended on a special reference frame called the ether, in a special medium in which the velocity of light was still relative to this medium. But in 1905, Einstein, with his special theory of relativity, he just concluded that this ether wouldn't exist. So, in fact, he postulated, and experiments afterwards verified that the speed of light, the velocity of light, if you wish, doesn't depend on any reference frame. We are talking about, of course, inertial reference frames. So in different reference frames, the velocity of light is c. That was originally predicted by Maxwell in his formulation of the electromagnetic field, and that's a very interesting thing, right? That the phenomenon that we are talking about, electromagnetic fields, electromagnetic waves, have a velocity that doesn't depend on the reference frame. That's not the same as other types of disturbances, like mechanical disturbances, sound waves, and so forth. Gravitational waves, for instance, they propagate with the velocity of light as well, velocity c, right? So there's some interesting things here. But we are not going to go through that. Right? That's a field of special theory of relativity. If you have accelerating frames, that's even more complex physics. in which you have to deal with the general relativity, and then velocity of light is not a very well-defined thing, you know. For instance, when you start coupling gravity with light, then you know, gravitational field may curve the light, may bend light, so massive objects might deflect light. That's a prediction of the general theory of relativity. But we are not in that, you know, in that field. We are just the traditional electromagnetism, and we are talking about standard situations. No massive gravitation has effects on the things we are going to talk about here. So going to more trivial things, putting the feet on the earth, you know, let's say, having our feet on the earth. Let's talk about our very simple physics of the electromagnetism. We are interested in situations in which the charge fluctuation, we know that charge fluctuation produce some effect, because we are going to show that. I mean, why is that? Because Maxwell's equations relate fields with their sources. And if the sources change with time, okay, we are going to see that we have some sort of electromagnetic disturbance that propagates in space. So we are interested in determining how fields relate to each in space. How do they depend? How fields depend on space and time? If we have a charge fluctuation in some point in space, and we are observing the effect far away from the disturbance, right? So in the region we are interested, we don't have any charge density or any current density. We are, let's say, in vacuum in the first approximation, right? We are looking, for instance, you have an antenna far away downtown, and we are here watching the TV, and we are trying to observe what is the field in our local position, and the currents are in the antenna, so we are far away from that. And let's say that we have vacuum in between, right? So let me just open my notes here. So then we have this situation. So what do we have? We have fields E and H. They are going to be the only variables because the electric flux density is a copy of E because of, you know, through this constant, the permittivity of vacuum. And B is a copy of H through the permeability, to the vacuum permeability. So when you do that in Maxwell's equations, let me just put my notes here. When you do that into Maxwell's equations, that reveal, I'm going to be exhaustive here sometimes, repeating the equations, you know. So let's put down the Maxwell's equations. We have curl of E equals to minus dB curly B dt, right? We call those rounded letters curly letters, let's say. Divergence of D equals to rho. These are the original equations. Let's make a tilted rho like that to remember that those are time-varying quantities. Divergence of B equals 0, and curl of H equals to J, which is the free current density, plus dd dt, and constitute the relations, you know, between D and E and P, right? Epsilon 0 E plus P. That's the electrical constituted relation, and B equals to mu 0 H plus M. So if we are talking about vacuum, which is the region of interest in our case, we are looking at this region here. There's no charge in this region, right? So then you don't have either P and M, and J is 0 as well, and rho is 0, right? And you have this relationship, D equals epsilon 0 E, so it's a copy of E, and B equals mu 0 H. So here we are going to have you know, mu 0 dh dt, right? This is going to be the divergence of epsilon 0 e. Epsilon 0 goes out, you can cut it out. This is going to be divergence of h equals 0, and here is going to be epsilon 0 dE dt, right? That's what happens. So all the equations are going to be represented by E and H fields. We're going to have an EH here with a constant, right? We have an E here, have an H here, and have an E here again. So what we have is this set of equations. Curl of E equals minus mu 0 dH dt. Curl of H equals to epsilon 0 dE dt. And divergence of E and divergence of H equals to 0. So you see that these equations gives the curl of E, which is proportional to the time rate of change of H. And here is the dual equation, just exchange parameters, unless of the constant that we see in the sign. But we see here that we have a similar equation. Curl of the other quantity is switched, right? So what we do, well, we are going to try to determine equations, to obtain equations in a single field quantity. To do that, if I apply the curl of H on both sides of this equation here, curl in both sides, we're going to have curl of H, which is related to the time rate of change of E. So I'm going to do that. So if we do curl of curl, right, put down the black letter here, curl of curl, right, which are the equations, we have curl equations of E or H. We have that identity, right? Gradient, gradient of the divergent of E or H. I can represent this, yeah, let's do like this. Minus Laplacian, the vector Laplacian, right, of E or H. That's what we get. Then we have equations for the divergence of E, it's right here, divergence of E, which is divergence of D, which becomes divergence of epsilon 0 E, or divergence of E is 0. And divergence of H is the same as divergence of B, because they are a copy of each other, is 0. So this term goes to 0, right? So the curl of the curl gives minus Laplacian of E and H, or H, right? On the right hand side, we have, you know, for instance, curl of E or H equals to minus mu 0 dH dt, or epsilon 0 dE dt. So the curl of it on each side yields minus mu 0 ddt of the curl of H, right? Over epsilon 0 ddt, the curl of E. Now this in turn is going to be, let's take a look here. Curl of H equals to epsilon 0 ddt, curl of E is minus mu 0. So what we have here, so this is going to give, this is epsilon 0, right? So we're going to have minus mu 0 epsilon 0, second derivative of E. And the other one is going to be minus mu 0 dH dt. So it's going to be also the same result, minus mu 0 epsilon 0 second derivative of H. So on one side we have this, on the other side we have that. So what we have here, you're going to have an equation like this, Laplacian of E or H. So we have a minus side on one side, the minus side on the other side, equals to mu 0 epsilon 0 second derivative of, let me just make it smaller. So we have, you see, we have uncoupled equations in this case. So what we have, well, if we call F either E or H, we have an equation that has a very interesting form. Let's call this parameter, you know, mu 0 epsilon 0. If we see here, this is dimension of field divided by L squared. Let's see the dimension of each equation, right? Before we go further, we have a Laplacian, the Laplacian of the field, right, equals to mu 0 epsilon 0 second derivative of this field. That's the equation we have. So dimensional analysis. Well, this is 1 over length square. This is field dimension, right? Dimension of mu 0 epsilon 0. So here we have 1 over t square, dimension of F. So the dimension of this quantity here is equals to time over L square, and dimension of the inverse equals to length over time square, which is velocity square. We're going to call this velocity equals to c square, right? Before we go even further, let's calculate this number. Okay? So what do we have here? The equation. This is 1 over c squared. Then we have an equation which is Laplacian of the field minus 1 over c squared times the field equals to a vector. So there are 3 equations here. I'm going to omit that arrow on top of the 0. So this is called the homogeneous wave equation. Okay? Why homogeneous? Because we have a differential equation, have a second order derivative in space, sorry, I forgot that, put here, second order derivative in time, right? And this is a homogeneous because there's no source, there's no stimulation quantity on the right hand side. That stimulation quantity would be a vector in this case here, okay? So because it's a vector equation. There are 3 differential equations in fact. So let's calculate, before we go, let's calculate this parameter, this number, what do we get, right? That's a fundamental quantity which is called the velocity of light in vacuum, because the permittivity is mu 0 and epsilon 0. So c squared is equals to 1 over mu 0 epsilon 0. The fascinating thing is that in 1905, when Einstein established a special theory of relativity, is that the speed, which is the speed of the disturbance, the propagation, the speed of the speed in which the electromagnetic disturbance propagates, doesn't depend on the framework. I mean, we are talking about frameworks, reference frames that move relative to each other with constant velocity. So if we measure physical phenomena, if we measure the speed of light in each of these frames, they the speed of light is always going to be the same. If you measure, mechanical traditional velocity of an object, then it's going to be dependent on the reference frame, but not the velocity of light. That's a fascinating result. In fact, it's a postulate. It's not the result, right? That's a postulate, so that's to fix all the physics involving, gravitation and electromagnetic fields. So, but let's go on here. We have, let's calculate that. Recall that mu0 is 4 pi times 10 to the minus 7 SI units, which is Henry per meter. Epsilon 0 approximately, right? I'm not going to calculate exactly, but approximately, is 1 over 36 pi times 10 to the minus 9. So we're going to have an approximate figure for this parameter C, farad per meter. So mu0 epsilon 0 is 1/9, right? So the product 4 pi times 1 over 36 pi is 1/9. 10 to the minus 16 SI units. So the root square, because this is 1 over c square, right? So it's 1 divided by 9 times 10 to the 16. So 1 over c equals to 1 over 3 times 10 to the 8 SI units. So the velocity of light equals to the well-known number, 3 times 10 to the 8 meters per second, right? That's the magic number we have, and that's the remarkable result obtained by Maxwell. You know that before Maxwell's formulation, people measured with relative precision the velocity of light, doing some sort of experiments, interference experiments, and so on. And they measured they already knew the velocity of light with relative precision. And Maxwell arrived at the same number that people had a figure very close to the figures, to the numbers measured by other researchers. So Maxwell was very fascinated to discover that his velocity c was equal to that same velocity of light measured by experimentally, right? So, okay. So, what happens? Suppose that we are in a rectangular coordinate system. Okay, let's go back to our wave equation. So yeah, we're talking about either E or H. They both satisfy the same wave equation, which is Laplacian of f minus 1 over c squared second derivative of f relative to time equals to 0. So let's use a rectangular coordinate system in which f can be written like this. Sum in 3 components. Let's say I goes from I equals to x, y, and z, right? So that's going to be AI, Fi. Now Fi is a component of the field. So if I use this rectangular coordinate system in which the versors are constant, right? So the Laplacian of f, in this case, specific case, is going to be sum of AI, because Laplacian is not going to act on AI. It's going to not actuate on AI. It's going to be Laplacian of Fi, right? And also, second derivative equals to the sum. Same thing, right? So we have, if we can assemble all the components together, it's going to be something like this. Sum AI, right? Laplacian of Fi minus 1 over c squared, second derivative of Fi, equals to 0. So we have 3 equations, and each equation, let's call Fi the wave function, right? Let's call it a psi function, scalar function. So we arrive at we have to satisfy the wave equation, the vector wave equation, by satisfying each component. So we have to satisfy the scalar wave equation. Let's call any component of the field. We call that this either EI or HI, right? So let's call it generically psi. So we have this equation, the scalar wave equation. That's the equation that has to be satisfied by either any components of the field. Every time you have a time-varying field, the time-varying field satisfies this, which is the scalar homogeneous wave equation. Okay? So let's solve it without a priori knowledge on how the fields change with time. We're going to solve it in rectangular coordinates independently on the way the fields vary with time. Okay, and that's a very nice way to look at the result. So let's look. So in rectangular coordinates, let's take a look on the general solution in rectangular coordinates. Okay? So let's call this function. In fact, we don't want to solve the problem. We want to see what special feature this function has. A function that satisfies the homogeneous wave equation has a special form. And we are trying to determine that special form without solving specifically what's the solution. So in fact, we want to determine what is there any special relationship between the coordinates and time for this type of disturbance that satisfies the homogeneous wave equation. So we are trying to find the connection. So let's call the connection between x, y, z, and t is a function w of the coordinates. So in other words, the psi is a function of the argument w, and w in turn is a function of x, y, z, and t. So let's calculate term by term the second derivatives relative to x, to y, to z, and to t. So let's start, let's make some chain rule here. We're going to do that. Then we're going to extend to all the other components. Let's make one of them. D psi dx, let's calculate it. So let's use the fact that psi is a function of w, okay? And w is some sort of function. We want to determine what's the form of w. What are the possibilities of w, okay? So let's calculate the derivatives, the psi dx. So the psi dx equals to df, right? Well, f is a function of one single variable w. So df dw, total derivative, partial derivative of w relative to x, right? And the second derivative of the psi is equals to d dx of this thing here, right? df dw dx. So use the chain rule. So it's the derivative of the second. Let's make the derivative of that one. So it's going to be df dw. First times the derivative of the second, d2w dx2, plus second, dw dx, derivative of the first, ddx, df dw. Here, ddx, df dw, in turn is derivative relative to w of the thing that is in brackets between parentheses, second derivative, the w2, then we have dw, dw dx, right? So that's the second term here. So this is d2f dw2, a first derivative dw dx. So I have this one, and that one gives a square. So we have the second derivative equals 2. So first term is the first derivative of f plus the square of this term here, this one and this one, right? And the second derivative of f plus second derivative of f. Then we have the w dx square. That's what we got. So if we do for the other ones, you know, if we put a y second derivative and second derivative, just put a, you know, second derivative relative to y, relative to z. Here is going to be relative to y and relative to z. So when we sum the three together, so we get the Laplacian, we're going to have, you know, in fact, it's the Laplacian of w, right? So it's going to be df dw. The sum of second derivatives is the Laplacian of w, okay? Plus the other one is going to be the sum of the squares with this common term here. Factor this out. Second derivative of w, you know, and you go to the sum of these terms, the w dx square plus the w dy square plus the w dz square. That's only the Laplacian, right? When you put time here, the same thing. Second derivative relative to time, here is going to be t squared, right? And here's going to be time. So we have another term which is going to be minus 1 over c squared df dw d2w dt squared, right? Minus 1 over c squared d2f dw squared, w2. Then we have the w dt squared. So that's what we got, equals to 0. Let's put this together. So, you know, these two are together and these two are together. So we have something like this. A coefficient of the f dw has Laplacian of w minus 1 over c squared d2w dt squared, right? Plus something that is the second derivative of f. Then we have sum of the squares. This is going to be a little large, so let's move to the next page. Copy. Go to the other page. So we have that. Right? The other term is going to be squares. So it's going to be something like this. The w dx squared plus the w dy squared plus the w dz squared minus 1 over c squared the w dt squared equals 0. Well, if you want, this is the magnitude square of the gradient of w, right? So let's do like this. So we make a compact notation here. The f dw, Laplacian of w minus 1 over c squared d2w dt squared. So this factor here is the magnitude of the gradient of w, magnitude square. So it's going to be plus gradient of W magnitude square minus 1 over c square dw dt square. I could generalize the nabla operator to include space-time together, but that's not going to do that, right? So this has a structure. If I define ct as another coordinate, I could make a 4-dimensional nabla operator, but it's okay. I mean, you can do like this. So this has to be 0. That's the equation we have. So, I mean, to solve this equation, what we need to do, I mean, given those f is the wave function, right? We have two derivatives, first derivative and second derivative. For me to balance this equation, this is a function of W here, I have to set both this term here equals to 0 and this term here equals to 0 as well. Okay? Both equal to 0. Right? So, in other words, W has to satisfy wave equation, which is nothing new, because, I mean, W satisfying wave equation, right? It's going. I mean, f is going to be the argument is something that also satisfies the wave equation. But the new thing is that this relationship also has to be 0. So what we have to do, we have to have this both conditions satisfied. W has to satisfy wave equation. That's nice. That's okay, right? We somehow expected that. It's nothing. It's not much new. But the new fact is this thing here: magnitude of the gradient of W square dw dt square equals 0. So we have to satisfy those two things, right? So let's look at possible forms of W that satisfy both equations, okay? So these are the two conditions. In the class notes, we wrote those in terms of the Cartesian components, but they can be written in compact form like this, okay? So we have to satisfy both relationships. So let's see each case. So that's what we get. I mean, in terms of, if we expand all the operators, we have something like that. Let me see if there's something wrong here. Okay, that's one equation here, right? Second derivative, which is this one. The other is the FDW. Let's look at possible forms of the argument, because that's what we are looking for. Let's try, first case, f is a constant. Okay? Well, if f is a constant, it means that f is psi, right? Psi equals to f of w. If f is a constant, it means that there is no disturbance in space or in time. We have a constant field, right? The field is constant everywhere. Of course, this is a solution of the wave equation, right? Because the wave equation has only derivatives. Any constant has 0 derivatives. So any constant is a solution, but it has no connection with any of the original disturbance that is producing the disturbance. So a constant is not a solution that we are looking for. Okay, so case 1, f equals to a constant. Nothing new. There's no, no meaningful result. Just psi equals to a constant is the result, right? This is just a mathematical solution with no meaning. That's not a wave, right? That's not a disturbance. Let's make a second case, case 2. The function is linear in his argument, AW plus B, right? in this case, what happens? I mean, f is a constant. I mean, just notice that second derivative equals 0 and the f dw equals 0, right? So in this case here, we have, for this specific form, we have the f dw is a constant, right? It's not 0. And the second derivative equals to 0. So I don't have both equal 0. But in this case, what happens? Well, because the f dw is not 0, what happens here? Let's see in your notation here, right? If the f dw is not 0, w must satisfy wave equation. That's what it means, right? You have, second derivative is 0, and the first derivative is not 0. So independently of this term is 0, and this is not 0. So w satisfies the wave equation. So it means that the case true is w satisfies wave equation. So this has to be removed, right? I mean, a constant element doesn't bring any property. So in fact, we have a solution something like this: f is proportional to w. So what is case true in fact? Well, w satisfies wave equation, so does f. F also satisfies wave equation. But what does it mean? It means that psi satisfies wave equation. But that's the original hypothesis. Psi has to satisfy wave equation. So there's nothing new here. Okay? So what do we do? So I'm going to show an example here. So what, for instance, let me just give you an example here, quickly, of case true, something that changes with time, but it's not a wave, okay? That's this example here. Let's assume we have this general form of W. We can eliminate the constant. I mean, that's the argument of the function, right? So f equals to W. But W is given by this special thing. I mean, I goes from 0 to 1, J goes from 0 to 1, and K and L. So I have a product of all the coordinates, X, Y, Z, and T. Either constant or linear function of one variable, or a product of two variables, or a product of three variables, or a product of four variables. Let's make the most general case. Assume that the solution equals to f equals to w, right? Equals to something like this, with unless of a constant, x, y, z, t. Right? I can have that. I can have this plus. I can do something like this: x, y, z, t, a plus b, x, y, z plus. Then I can make permutation and do several products. Okay, so let's just do one term only. So is this a wave? Solution that has this dependence satisfies wave equation. Right? But it's not a wave. Okay? If I make y constant, z constant, and t constant, then a psi is proportional to x, for a given time. So if we make a plot, sorry about that. If we fix at a given time the coordinates y and z, the function is a function of x, right? The wave function. It's going to be a function of x. It's going to be something like this. So this is field, E or H. Energy goes with the square of the field, right? So the square of the field is going to be a parabolic behavior. So that's energy density. By chance, we are using the same the same symbol. Let's see. This is WE or WM, which is energy density. The energy goes with the square of the field infinitely and grows indefinitely. That's not a wave. There's no such a infinite amount of energy, right? So that's not a meaningful result, physically realizable result. And also, there's no propagation. We have some field distribution that is stationary, doesn't propagate, just something that is standing there and grows indefinitely. That's a solution of a wave equation, right? But it's not a wave. Okay. So let's go to the final case now, in which really both the second derivative, which is that's the one I spoke before, right? Case 3, we have both coefficients not zero, first derivative not zero, and second derivative not zero. So one thing is W satisfies wave equation. And the other condition is that the gradient square, right, minus 1 over c square I'm sorry, yes, the W, right? I'm talking about W, yeah. Sorry about that. Let's do it again here. So nabla of W square equals to 1 over c square dw dt square. We're talking about real functions at the moment, because we are in the real physical world, right? Our mathematical functions are all real. There's no complex numbers here in the real world. We are talking about real fields in 3D space and time. No complex fields. Complex fields are just mathematical tools that we use to calculate the real fields in the 3D space. What we have is that the gradient is a constant vector, right? That's the only possibility. The gradient must be constant, and which is a replica of the w dt, which also, if I choose the gradient a constant vector, and the time derivative also constant value, I can satisfy this equation, right? So all for me to satisfy this equation is that gradient of w is a constant vector, let's say a, right? And let's call the dw dt, let's call this is a different letter. Not a, let me call it, yeah, I think you can call a g, a vector g, okay? Constant vector, g is constant. And the w dt I'm going to call a constant d times c. So if I choose gradient a constant vector, and the first derivative a constant value, so this is going to be equals to d squared. So what happens, magnitude of g, so I'm going to have g, so if I put that in there, it's going to be g is the magnitude square equals to d squared. That's all is required for me to satisfy this equation. Well, let's call g with components a, ax, plus b, ay, plus c, az. So what we have to do is that if I plug that into that equation, it's going to be a squared plus b squared plus c squared equals to d squared. So I have to choose my constants. I have to use the gradient of w has to be a constant vector, right? And the constant vector G has components AAX, BAY, and CAZ. And the derivative of W has to be D, a constant, times the velocity of light. So in this case, I have this relationship has to be valid. That's all I have to do is to choose the constants. So when I have both the first derivative of f not 0 and second derivative not 0, if I do this choice, I satisfy both wave equation, right? And also, because you see, it means that when I make this special choice, it means that the gradient of W equals to G implies that the W dx is a constant equals to A, the W dy is a constant equals to B, and the W dz is a constant equals to C. What happens here? And the W dt is a constant, which is D times C. So what happens here? The second derivatives are all of them are 0. So it means that W satisfies wave equation. And also have this additional restriction that W has a constant gradient. So in other words, something like this. So let's determine now, I have differential equations for W. Let's determine W, okay? So the W dx equals to A, right? If I integrate on both sides, W is going to be AX plus a function of Y, Z, and T. Let's call that G1. Not Y, X, right? Y, Z, and T. Then we go and plug on the second equation. The W dy equals to B. But W is given by this one. So the W dy is the derivative of G1. dg1 dy equals to B. Second integration now. G1 equals to By plus G2 of Z and T. Right? So now we go dW dz. Now we see that now W has the form AX plus BY plus G2 of Z and T. Now the W dz is the derivative of this relative to Z, so it's going to be dg2 dz, which equals to C, right? So it means that G2 equals to CZ plus, plus, right? Plus G3 exclusively a function of time now. So finally, the W dt equals D times C. So if you make the derivative here, it's going to be total derivative equals to D times C. So G3 equals to dCt plus E. Right? So that's what we got. So what we have here, if you look at what are we doing? We are determining the specific form of W, right? AX plus BY plus CZ plus dCt plus a constant. So that's the general form that we obtain, for this solution. That's the argument of the function. AX plus BY plus CZ plus dC times T, provided that D square is the sum, right? There's another constant here, but that's not going to be important, in fact. D square equals to A square plus B square plus C square. So if in vector form, these are the coordinates of the vector, position vector, and these are the components of the vector G, right? So W has the form G dot X right? Which is this term here, plus this term there, dct plus E. That's the general solution for the argument. I mean, to satisfy wave equation, the simplest form of the argument of the function is this linear function of x, y, z, and t, right, plus E. So if you want to write in terms of coordinates, it's something like this. The function, the wave function, or if you want, psi of x, t, equals to w so it's going to be w equals to not w, sorry, psi, right? It's going to be a function of g dot x plus d, which is root square of a square, or if you want, magnitude of gradient of g, which is constant, square. I mean, magnitude of gradient, which is d, right? This is the root square of a square plus b square plus c square. So it's, sorry, magnitude of g times ct plus a constant, right? I'm going to drop this constant because that doesn't give any information. It's just a shift in the coordinate system. That's what it is. Okay? So let's make that constant equal 0. So that's the form of the wave function. It's a function. The argument of the wave function is a linear function of the coordinates and time. Okay? So I could put here plus E, but I mean, it doesn't give, it's just a shift in the coordinate system. Okay? We are looking at the general behavior of the wave function. So let's drop that E, that constant term. Right? So why is it called a uniform plane wave? Well, let's make a choice such that let's make a change here. Just to understand what does it mean to have this argument here. Let's call, let's make g into minus g. So it means, so g is going to be changed to a new form, because I don't know who are the constants, right? Who are a, b, and c? Well, I don't know the sign. So let's make specifically, reverse the sign. So it's going to be minus a, ax, minus b, ay, minus c, az. So when we do that, so we are going to have, I'm going to, here I'm going to put again, this is d, right? So the function is going to be something like this. I'm going to put the dc in, you know, as a factor. I'm going to factor out this thing here. Still going to use this thing here. So when I do that, I'm just going to make g into minus g. So it's going to be t minus gx over. So g is still ABC, so I should use minus g divided by let me see here. So this is going to be divided by magnitude of g, right? Times c. Correct? That's what it is. Okay. Well, I'm going to make this thing here. So you see that g divided by magnitude of g is a unit vector, okay? So c equals to f. I'm going to still keep it, g times c t minus a versor. Okay, this is a versor. G divided by magnitude of G is going to be called versor U. Okay, so it's going to be t minus u dot x divided by c. That's the way the wave function behaves. Okay, right? So that's the form of the wave function now. Very more nice, aspect of the form of the function. It's something like f of magnitude of g times c t minus u dot x over c. Right? That's the formula for the wave function. Let's make this equals to 1. So we can, this doesn't matter. We just want to make, this is a constant number, right? It's a scale factor. It's not going to change what the result of the analysis. We want to see the behavior of this function, how it behaves in space. So let's make gc equals 1. So it's going to be psi equals to f of t minus u dot x over c. So that's the form of the wave function, right? So u is a versor that has 3 components, right? ux plus ui plus uz, and the sum of the squares equals to 1 because it's a unit vector. Okay? So the question is this is the form of the function. How does it move in space? Does it change in space, this function? Well, it changes, right? In time and space. It's a function of 2 coordinates. Well, if we ask the question, what's the locus of points in which the wave function remains constant? Right? The amplitude of the function is constant. So if we make this a constant value, we are going to have a constant amplitude. So what's the relationship? We are going to have a relation between x, y, z for each time point. So at a given time point, a relation between x, y, and z in 3D space is a surface. So the question is, for a given time, what is the surface that gives a constant amplitude of the wave? That's the question. Right? Well, let's see. At time t equals to a given time, constant value, we have a constant value of this argument. Let's call it k, t minus u dot x over c equals to k, right? So let's move the time. Let's let's make time moves for a new time t1 now. And I want to know, where is this surface now? This is one surface, right? We are going to look at it in a moment. This is one surface. When I change the time, I want to go to a new time. I want to have I want to know where is the surface now that gives the same amplitude. So I'm going to T1. So this is lots of points x1, which I have to determine where is it, divided by c, equals to the same constant value. At time t2, I'm going to t2 minus u dot x2 over c is the same value k, right? So that's the first surface at time t1. That's the surface at time t2. The surfaces give the same amplitude. So let's calculate the time change, delta t equals to t2 minus t1. So if you calculate that, what happens? It's going to be, unless of that, so if I subtract those two here, so I'm going to have T2 minus T1. So if I subtract those two things, right? So you're going to have delta T. So K minus K equals 0. So I'm going to have minus the difference between those two. I can move to the left hand side, to the right hand side. It's going to be 1 over c u dot x2 minus x1. Right? So that's the condition. The surfaces, there's a time difference. There are two different surfaces, and they have to be tied by this equation. Okay? So that's the condition. U dot u over c, or let's make u dot x2 minus x1 is a constant. Okay. Well, u is a constant versor, points to a given direction in space. Who determines u? Well, depends on the emitted field. The field is emitted by some radiation source. For instance, it might be a directional source that, this verse is going to have a meaning that is related to the direction of the emission, of the emitted radiation, right? So if I align the difference vector, so I have x2 and x1 in space. So I have a lox of points x2 and a lox of points x1, right? So all the points on x2 are on a surface, on a wavefront. All of the points on x1 on a given surface, all of the points on x1 on the surface has moved to a new place. So if I align x2 and I have, let's say, I have a u here, right? If I align x2 minus x1 along the same direction of u, so let's make on the same direction. So let's say that x2 minus x1 is a difference in length, right? Delta L, the difference in different length, times u, right? So that means that the logs of point x2 and the logs of point x1 have a time difference, delta t, and the distance between those surfaces, delta L, along the u direction. So I'm going to have delta L, u dot u, right, equals c delta t. So in other words, delta L, delta t equals to c. So the surface has to move along the direction of u with the velocity c. Okay? So we don't know what the surfaces are yet. We are just saying that, well, giving a direction, the logs of points on the first surface, x1, and the logs of points on the second surface, x2, if I subtract the two vectors, and along the direction of u, the surface has moved along that direction with the velocity c. Let's determine what are those surfaces. So that's the velocity to maintain a constant amplitude. So the surface has to move along the u direction with the speed of light, c. Okay? Well, what's the logs of points? Let's go back to the original equation, right? T minus u dot x over c equals to a constant. What is this? At a given time, right? Well, let's put this equation like this. U dot x equals c times t minus k. It's a constant. So the equation of the surface u dot x equals to a constant. What type of surface has this property here? Let's see. That's u. Let's make a 3D system here. Well, let's make it almost 3D. Let's make it like this. I'm going to line, okay? This is the u direction. So u is like this. So we have a coordinate system here. This is not any specific direction, okay? It's just the U direction. I'm just aligning to the right. So so let's put in 3D space now. Let's put the x vector. Logs of points that x projected along U is constant is the logs of points that end on a plane, right? Well, all the points on a plane that's orthogonal to U. Maybe this is not a good drawing. Let me make a new one. Let me make a new drawing. I'm gonna. It's better to make a 3D plot. Let's make arbitrarily in any direction. It's better. Let's make it like this: X, Y, and Z. And Y, right? Sorry, X here. X, Y, and Z. So in this, maybe I make a cube. It's going to be easy. I'll make a cube here. Something like this. Let me put my U vector. I hope it works. Along this direction here. So if I pick any x vector in space, well, the logs of points in which x projected along the U direction is constant is a plane that's orthogonal to U. Any vector that ends with the tip on a plane orthogonal to U, any vector that has a tip that ends on a plane orthogonal to U has a projection along U which is constant. So I'm going to make this plane, okay? Let me try to make like this, another color here. I'm going to make like this. Not like that. Something like this. I'm going to make a small part of this plane. Stuff like that, okay? So I'm going to continue here. That's the direction of U, okay? These are two directions along the plane, the blue plane here. Let's make this like this. So we have a 90 degree here, right? So this plane here, I hope it's clear. I'm going to show you the drawing, just trying to construct before showing the whole thing. So we have a plane. Every vector that ends on a plane that is orthogonal to U has a constant projection along the direction, right? So it's something like this, right? Plane, U direction. Just look at the projection on the paper, right? Any vector that ends on a plane orthogonal to U has always the same projection, which is this smallest length vector here. So all these vectors, so these are logs of points such that x dot U is constant. Right? So in other words, the logs of points in which the amplitude of the wave is constant is a plane orthogonal to the versor U. Something like this. Right? Here we have the U direction. Here we have one plane at t equals t1. We just derived that, right? We have the second plane at t equals t2. Both are orthogonal to U. And we have x1 is the tip of the first vector ends on the first plane. The tip of the second vector ends on the second plane. This is the vector difference vector. And the projection of the difference vector along u is this, delta L, which is the velocity v equals c times delta t. So the wavefront is a plane that moves with the speed of light in vacuum. And the velocity obviously equals to 3 times 10 to the 8th meters per second, right? So what we have here, so let's see, this is called the uniform plane wave, because the wavefront is a plane, and on the plane the amplitude doesn't change, so the amplitude is uniform, it's constant, okay? So that's called the uniform plane wave. Let's do some remarks here, which are very important. Well, we have obtained one type of solution we call psi plus, even though we don't need, in fact, because we use vectors, And vectors point to the direction where things will happen. So, but let's do that difference now. Then we are going to get familiar with the notation. Then we are not going to need that anymore. But the psi plus is the solution when I have a minus here. That was a specific choice, right? That means a wave that moves in the direction of u. Okay? With velocity c in the same direction. If I reverse the sign of u, okay, then I would have the argument of the function would be t plus, like this one here. So you obtain another type of solution, it's psi minus f of t plus, right? Well, what is this? Well, this is equals to minus u. So that means it's a wave that moves in the direction of the minus u versor, in the opposite direction. That's the second solution of the equation. I have two solutions, one that moves to one direction, one that moves to the other direction. In other words, if I have an antenna here, let's assume that the world is just two-dimensional, right? One wave is going to move to the right and the other to the left, right? So two solutions. So they move away from the source. So that's called the uniform plane wave because of that feature of the plane over which the amplitude is constant. So that's the solution. Even though we don't know at the time how the fields depend on time, we have a general behavior. That's a disturbance. Something. Of course, the plane wave doesn't exist. It's just idealization. Why? Well, because the plane occupies an infinite extension. We would have to have an infinite energy, right? So we cannot do that. But I mean, at least we know the feature. And plane waves, when we start considering harmonic fields, plane waves are the Fourier components of any wave disturbance, right? So they are idealized mathematical tools that can be used to decompose real functions into those Fourier components, as we do that in linear system analysis, when we can decompose function in Fourier components, or we can make Fourier transform and so on, right? That's the same behavior, the same principle. Let's now look at the final part of the lecture. We are interested, of course, I mean, any system, we want to determine, devices are built to operate on a narrow range of frequencies sometimes. They are specifically for a given frequency around a frequency range around the central frequency. You can, of course, you can design wideband devices that work on a wider band, okay? But even so, we have to determine what's the behavior of device for a given frequency and how that behavior changes with frequency. So it's important to study Maxwell's equations in the harmonic regime, in which the frequency is well known. The time change, the changing time, is a periodic function with a well-behaved behavior. Okay, so let's look into that. Maxwell's equations for harmonic fields. Now we are going to have the time variations going to be assumed known. We are going to have angular frequency omega, in which that defines the periodicity of the function. The functions are going to have the behavior like sine or cosine, right, of omega t. This is a dimensional number, omega t, correct? But this has a meaning in trigonometry. This is angle, or angle, but in electroengineering you call this phase. And phase is adimensional, but has a meaning, has some degrees or radians. So this thing here, omega t, it's not a unit, but is either degrees or radians, right? But we are going to use the number. The number is radian. So it means that the unit of this quantity here is radians per second. So this is called the angular frequency in radians per second. Well, you can also define a number of turns, right? If you have a numbers of turns per second, for each turn, each cycle, you have a total change of 2 pi radians. So this f here, this scale factor, 2 pi f, is called the frequency, the traditional frequency that we measure in cycles per second, or hertz. And if we look at the behavior of the temporal function, how the quantities change in time. So we have a periodicity. Well, the period is given by t, which is the inverse of the frequency, right? After one period, you have, the argument of the function is something like, let's say sine of omega t equals sine of 2 pi f t, right? So when this equals to a multiple integer value, so we have a repetition, right? So for a given period t, f times t equals to 1 gives a repetition of 2 pi. So period is the inverse of frequency in cycles per second. So let's record the terminology, because we are going to have temporal frequency and spatial frequency. Okay, we are talking about temporal variation. So the frequency, this is called the frequency in hertz. Sorry about that. There's something here in my screen. Okay. Frequency in hertz, right? That's called frequency. That's measured in hertz. Never mix f and omega. And omega is the angular frequency. So there's a 2 pi factor between them. If we mix things, so we have an angular frequency, which is radians per second. So that's cycles per second, right? And radians per second. So let's write down Maxwell's equations, assuming that we have harmonic fields. What are we going to do? Our field quantities are function of x and t, right? They generally have, periodicity, and we can always write this using complex algebra, as the real part of something that is exclusively dependent on x, which is we are going to call the straight, the block ladder we are going to use to represent something that depends only on the coordinates. And then we have j omega t here, right? So we always can, if you have harmonic fields, can always use complex algebra to determine the real field by using this prescription here. So we introduce The complex vector f, you know, we have a new type of vector. We have to be very careful with complex vectors, right? They don't have, I mean, a geometric representation like the physical vector. These we can draw it, you know, in space. These we cannot, because they have a real part and imaginary part. What are they, right? It's complicated. It's not simple. So you see, so I can just, let's look into what this is. Well, f is a function of the coordinates only. So it's a block ladder, like this one, straight f, right? It doesn't depend on time. It's exclusively dependent on x now. I know that dependent on time already. Okay, so fx would be some fx ax. This is our complex numbers now, fy ay plus fz az. So what is f of t? So just calculate here. F of xt. So these are all functions of the space coordinates. So it's going to be the real part of, I'm going to make it like this to make it simple, right? Sum I equals x to z of ai. Well, in this case, the ai's are real numbers. Sometimes we might play with the versors using complex versors too, but I mean, for now, I'm decomposing in real versors, okay? So we're gonna use that. It's gonna be fi exponential of j omega t, okay? So fi is a complex number which has a magnitude and a phase. Let me call it phi I, the phase of the ith component. So just to give you an idea of what the complex vector is, okay? We're not gonna be doing that all the time. Just make sure we understand what we are doing here. So this thing here, I mean, this is a function of coordinates. This is a function of coordinates. Okay. So this is gonna be so this is a complex number, magnitude and phase. So it's gonna be real part of sum plus phase. So I mean, that's easy, right? That's going to be ai. I'm sorry. So I can calculate now. It's going to be sum ai magnitude of fi. Then we have real part of this function here is cosine of omega t plus phi I. So that's what we have. We have an harmonic field. F xt equals to sum I equals x through z ai fi magnitude, right? Which is a function of the coordinates times cosine of omega t minus phi I of x as well, right? So these are functions because this is a part of the function fi. So that's how it looks, how the field, the physical field looks like. It's an harmonic function of omega. We know already it's going to change in time with the frequency omega. It's complicated. You have several components. You have different phases. The phase depends in space, coordinates, might not depend as well, might be constant phases. So I'm just saying that in general, that's how it behaves. Okay, that's how the field behaves. So writing f like this, in other words, writing f as the real part of a complex vector that depends on the coordinates in this form and times the complex function exponential of j omega t gives me the right harmonic field. I mean, that's a field that I know a priori that changes in time with a given constant frequency omega. Okay, So that's what I have to say for you to understand how a complex vector, what it gives in time. So never write a complex vector in the physical world. Okay, this belongs to the complex world. Okay, the imaginary world. That is a tool that we use to calculate the physical world. We have to bring back to calculate the real part before doing things. Okay, so you never put this, never write like this. A field is given by, as many textbooks do. That's very wrong. We don't have a complex vector in the real field. Never write f like this, f of x exponential j omega t. This is wrong. We don't have fields like this. This doesn't exist, right? It's not a real field. If this is complex, this cannot be written like this. This is a real field. This is not a real field. So we have to write like that, real parts. People sometimes do that just by notation, but we have to. But I mean, people who don't understand very well the notation start thinking that in the physical world we can write that, and that's not true. Okay, that makes a mess if you start playing with those things. So be careful. So what happens to Maxwell's equation? Let's say one equation like this: curl of E equals to minus, sorry, I'm already writing the equation in complex form, dB dt. So if we write E equals to a real part of E of x, I'm going to drop the dependence on the space coordinates. I'm going to write like this. H equals to the real part, B, so it's block letters for all the field quantities now are complex vectors. So in other words, either E or B can be written like this. E can be written as half of E plus the complex conjugate. So this is here is the conjugate of E, exponential j omega t. Well, how do I calculate the conjugate of a vector? Well, go to the original definition here. You go here, right? Conjugate of a vector is the conjugate of each component. If you are decomposing the vector against a real basis, sometimes we can use complex versus, but I mean, if you do that, it's just a complex, I mean, it's just the conjugate of this. Otherwise, the conjugate of the whole thing. Okay? But I mean, if you have real versus, it's just the conjugate of the components. That's how you calculate the conjugate. So I can always write the E or B field, right, the same way. Right? Then I plug those back into the Maxwell's equations for Faraday's law. What do I have? Curl of E, well, this is space derivative, doesn't act on the time function. It's going to be only curl of E, plus the complex conjugate. We don't have to care about that. ddt is going to be only the derivative of the time function. So let's see how it works. Curl of E equals to curl of 1/2, right? Of E exponential j omega t plus complex conjugate, which equals to 1/2 curl of, I can put outside, exponential j omega t curl of E exclusively, right? Plus complex conjugate, which is going to be 1/2 of ddt minus mu0 j omega t plus complex conjugates. So this is going to be 1/2. Well, the derivative goes directly on the complex function here. It's going to be 1/2 of minus mu0. So the derivative is j omega, right? Times the function. So it's going to be So let's now balance the equation. You have this thing here equals to this. So 1/2 I can cancel, right? So you have exponential of j omega t curl of E plus the conjugate equals to minus j omega mu 0 b exponential plus complex conjugate. So in other words, if this equals to that, the complex conjugate is automatically satisfied. So to satisfy this equation here is just enough to balance this term with that one, because automatically we have the complex conjugate satisfied. So when we do that, we cancel the ag omega t, and we're going to have an equation in this form. Curl of E equals minus j omega. That's vacuum. I'm sorry, there's no mu 0 here. I'm sorry about that. Why did I put a mu 0 without any reason, right? That's not h. Minus no mu 0 here. Sorry, no mu 0 there. No mu 0 here. So that's the Faraday's law in differential form, independent of the medium. So now we have only space derivatives, space functions of space coordinates. E and B are functions of space coordinates only. Okay? So in practice, what we do, we replace the physical fields by the phasor, the vector, complex vectors, or B, or H, right? Or everything. All the field quantities are going to be block ladders, straight, E, B, and D, and etc. And every time we see a derivative, we replace, like we did here, by j omega. That's the rule that we have. So there's no time variation. The equations in the harmonic regime are equations that express space derivatives of vector functions that are exclusively dependent on the space coordinates. So then I'm going to just write down, right? Curl of E, that's the first one, equals minus j omega b. Divergence of the complex vector D, block ladder, equals to rho. So what is rho? Well, just recall here, put it on the side. The tilted rho is the real part of straight rho exponential of j omega t. This is only a function of coordinates. This is a function of space and time. So we have a change in notation here. Let's make a nice straight rho here. Okay, free charge density, which is a function of x only. Curl of h, straight h, dependent on the coordinates, equals straight j plus, well, d dt is j omega d phasor d, complex phasor, right? Complex vector. And finally, divergence of b equals to 0. The four equations assume this form now, this shape. Constitutive relations are replaced by the corresponding constitutive relations between complex vector quantities. D straight equals to epsilon 0 E straight plus P, exclusive functions of x, right? B equals to mu 0 H plus M, and whatever relation we got for J and E, if we have, okay? And also, we can conclude just showing you the boundary condition. I mean, it's a straightforward extension, but just, same thing that we had before. Now we only have, relations, between, if you have a boundary between two different regions, an interface, if we call the fields on one side by subscript 1, fields on the second side of subscript 2, well, we have the same, the same boundary conditions now involving the complex vectors. N cross N, the normal cross E2 minus V1 equals 0, tangential field is continuous. Doesn't mean tangential, right? Because the E field is not a geometric entity. So I cannot even draw it in space. Because E field, each component has two numbers, real and imaginary parts. So, but I mean, you can say, because we have this, we are used to say, right? That would mean in phasor form, I mean, in the real world, that E field has a tangential component that is continuous. Okay. Here the same thing. You have a surface current, which is a complex vector, and also discontinuity in the normal components of the physical field equals to rho s complex number function, and B normal is continuous in the physical world. Okay. So that's what we have for Maxwell's equations in the harmonic regime. And that concludes our lecture for today, and we continue on next lecture. Okay, I hope to see you then. Bye-bye.